Have you ever looked at the night sky and thought about what lies in its veil? The universe lies beneath those crystal clear, twinkling stars. It is complex and incomprehensible. Welcome to the dark side of the universe, where syllables like dark matter and dark energy make even more sense. What we can view is merely a tiny part of what is out there. However, these in your dreams creatures make up around 95% of the universe, but still cannot be seen with the naked eye. This begins the interesting part. Traveling with us on a great adventure, an adventure where we will try to solve the mysteries of dark matter and dark energy, which govern not only the galaxies but also the universe as an entity. Are you prepared to embrace the darkness? Then, together, we will cut through the dark. Introduction to the dark universe. Envision a clear night away from city lights, where the sky becomes a huge canvas of glittering stars, a brilliant moon, and faraway planets. As you stare skyward, you feel a profound connection to the universe, attracted by its beauty and mystery. For thousands of years, mankind peered at these stars and assumed we understood what existed. The planets in our solar system, the glittering star clusters, the swirling galaxies, and the clouds of cosmic dust. It appeared straightforward. If you could see it, it was there, and if you couldn't, it wasn't. But as the centuries passed, our curiosity led us to craft more powerful tools. Telescopes that could see beyond the limits of our eyes, detecting light invisible to us. We peered deeper, pushing the boundaries of knowledge and discovering countless wonders. Yet, these advancements brought about an unexpected mystery, something that seemed to defy all logic. Galaxies, those immense collections of stars held together by gravity, were behaving strangely. The stars on their outskirts moved far too quickly, as if some unseen force was holding them together. It was as if we were watching a play on stage, but the spotlight only revealed half the scene. Shadows hinted at characters we couldn't see, influencing the story from the darkness. The more astronomers studied the universe, the more they realized that what we saw, stars, planets, gas, and dust, made up only a small fraction of the cosmos. In fact, a staggering 85% of the universe was completely hidden, invisible, and undetectable with our traditional instruments. This hidden mass became known as dark matter. It doesn't emit light, reflect it, or block it. It's simply there, exerting gravitational pulls, influencing the movement of galaxies, and holding together cosmic structures like an invisible cosmic web. But even that wasn't the end of the story. Observations of distant supernovae revealed an even stranger phenomenon. The universe was not just expanding, it was accelerating, driven by a mysterious force pushing galaxies apart at ever-increasing speeds. This force was dubbed dark energy, an enigma that defied the laws of physics as we understood them. Suddenly, the universe felt far more mysterious, like a grand cosmic puzzle where the pieces didn't quite fit. What we had thought was a complete picture was merely a sliver, a thin veneer covering a far stranger reality. Beneath the surface of our familiar cosmos lay the dark universe, a realm composed of dark matter and dark energy that we couldn't see, touch, or measure directly. Yet its influence was undeniable. It was shaping the cosmos, steering the galaxies, and determining the ultimate fate of everything that exists. In this journey, we'll venture into the shadows of the universe, where our understanding of reality bends and twists. We'll unravel the invisible forces that sculpt galaxies, discover how scientists came to realize that most of the universe is hidden from view, and explore the implications of living in a cosmos where darkness rules over light. As we dive into the mysteries of the dark universe, prepare to have your mind expanded, for what lies ahead challenges everything we thought we knew about the nature of existence. The composition of the universe. Think about the cosmos as a massive cosmic recipe, with each ingredient painstakingly measured, mixed, and combined to form the immense expanse we know as reality. For ages, humans assumed that the elements were straightforward: stars, planets, dust, and brilliant gas clouds dispersed over the night sky. However, as our understanding grew, we learned that this familiar cosmos was only the frosting on the cake. Below the surface lurks a considerably more intricate recipe with elements we can't feel or touch. To truly grasp the composition of our universe, scientists needed to break it down, to separate the known from the unknown, the visible from the invisible. What they uncovered was astonishing and, frankly, a little unsettling. Ordinary matter. Everything from the Earth beneath our feet to the distant galaxies light years away accounts for only 5% of the universe's total composition. This is the visible universe. The stars that twinkle in the night, the planets that orbit our sun, and the galactic arms that spiral gracefully in the depths of space. It's the matter we can see, measure, and interact with. The familiar building blocks of atoms and molecules that make up our world. But the story doesn't end there. Like the dark depths of an ocean, most of the universe lies hidden beneath the surface. Scientists discovered that a mysterious form of matter, which they call dark matter, makes up roughly 27% of the universe. This dark matter is completely invisible. It doesn't emit light, doesn't reflect it, and doesn't interact with the electromagnetic forces that govern our matter. Yet it has mass. It pulls, tugs, and shapes the cosmos with its unseen gravitational force. It's like a silent puppeteer, controlling the dance of galaxies and acting as a glue that holds them together. Without dark matter, galaxies would fly apart, their stars spinning off into the darkness, unable to maintain the beautiful structures we observe through telescopes. But if dark matter was a surprise, then the next discovery was a revelation. A discovery that would rewrite the very nature of reality itself. In the 1990s, astronomers observed distant supernovae and found something they didn't expect. The universe wasn't just expanding, it was accelerating. A mysterious force, one that didn't fit into the known laws of physics, was pushing galaxies apart faster and faster. This force, dubbed dark energy, makes up a staggering 68% of the universe. We can't see it, touch it, or measure it directly, but we know it's there by the way it affects the expansion of space. It's as if the universe has a hidden driving energy, a cosmic wind that inflates the fabric of space itself, pushing everything apart in an ever-growing dance of separation. The discovery of dark energy transformed our understanding of the universe's fate. It's not just the empty void between galaxies. It's a mysterious, ever-present force influencing the very structure of the cosmos. The more we observe, the more we realize that this dark energy might determine the ultimate destiny of everything, from the smallest atom to the largest galaxy cluster. So here we are, staring at the true composition of the universe. Only 5% of everything is what we can observe, a mere sliver of reality made up of familiar matter. The remaining 95% is hidden in shadows, a cosmic enigma composed of 27% dark matter, the unseen scaffolding of the universe, and 68% dark energy, the invisible force driving its expansion. Imagine standing in a brightly lit room with 95% of the light suddenly dimmed, revealing shadows and shapes you never knew existed. This is our universe. A place where the known is just a tiny island in an ocean of the unknown, and where the mysteries still lurking in the dark are far more significant than anything we've ever imagined. The halo of dark matter, an invisible mass that extended far beyond the visible stars and gas. This dark matter didn't glow, didn't interact with light, and didn't emit any form of radiation. It was simply there, its presence revealed only by the gravitational pull it exerted. Rubin's work was a turning point in modern astronomy. Her observations provided the first concrete evidence that dark matter wasn't just a speculative idea born from mathematical inconsistencies. It was real, and it was everywhere. Spiral galaxies weren't behaving oddly because of some cosmic anomaly. They were responding to a reality we couldn't see, but that was profoundly influencing everything we thought we knew about the universe. Her discoveries were revolutionary. They confirmed what Fritz Zwicky had suggested decades earlier, that the visible universe was only a fraction of the whole story, and that galaxies were surrounded and shaped by this invisible substance. Rubin's work showed that dark matter wasn't limited to a distant cluster like Zwicky's Coma Cluster. It was a universal phenomenon, present in every corner of the cosmos. Every galaxy she observed, whether close or distant, displayed the same strange behavior. Stars were orbiting at speeds that visible matter alone couldn't explain. The revelation was profound. If every galaxy was encased in a halo of dark matter, then dark matter wasn't just a small curiosity. It was a fundamental component of the universe itself. It was the invisible scaffolding upon which galaxies were built, the hidden force dictating the movements of stars, gas, and everything in between. Rubin had uncovered not only proof of dark matter's existence, but had shown that it shaped the very structure of the cosmos. Her findings turned what was once a fringe theory into mainstream science, and dark matter became a cornerstone of our understanding of the universe. No longer was it a whisper of doubt or an academic curiosity. It was an essential part of the cosmic puzzle, a puzzle that astronomers are still piecing together today. Rubin's legacy is one of perseverance and wonder, a testament to the power of observation and the courage to challenge the status quo. The discovery of dark matter was a reminder that the universe is far stranger and more complex than we ever imagined. We live in a cosmos where much of reality is hidden in shadows, where the things we can't see hold more sway than the things we can. Thanks to Rubin, we now understand that the stars are only the tip of a cosmic iceberg, and that the vast, invisible forces of the dark universe govern the grand dance of galaxies, guiding them silently through the infinite darkness of space. The properties of dark matter. Dark matter is the universe's greatest enigma, a force as mysterious as it is pervasive. It lurks in the cosmic shadows, hiding between the stars and galaxies, a silent presence that neither shines nor dims, neither flickers nor fades. For all our technological advances, from the humble telescope to the cutting-edge observatories that scan the universe, dark matter remains completely invisible, hidden from every instrument humanity has invented. We cannot see it, touch it, or capture it, yet we know it's there because of the way it bends and pulls on the visible universe, revealing itself only through the subtle force of gravity. Ordinary matter, the stuff that makes up you, me, the Earth, and every star in the sky, interacts with light. It can absorb and emit energy, creating the spectacular nebulae, glowing galaxies, and shimmering stars that fill the cosmos. Dark matter, on the other hand, is utterly different. It doesn't emit any light or energy, nor does it reflect or absorb it. It's like a cosmic ghost, passing through the universe without leaving a trace, except for its gravitational influence. It's the unseen hand that shapes the universe's largest structures, pulling galaxies together and guiding their formation. Unlike ordinary matter, dark matter doesn't cluster or clump. It doesn't form into dense, compact objects like stars or planets. Instead, it exists in vast, diffuse halos that envelop galaxies, creating a kind of invisible skeleton that defines the boundaries of our universe. Imagine a galaxy as a pearl sitting within a gigantic unseen bubble, the dark matter halo. This halo extends far beyond the visible stars, stretching out into the emptiness of space, binding the galaxy with its subtle but persistent gravitational pull. Without this dark matter halo, galaxies would not hold their shape. Their stars would drift apart, unable to stay bound together. Scientists have spent decades trying to unravel the nature of this invisible force, proposing various theories about what dark matter could be. Some believe it consists of WIMPs, or weakly interacting massive particles. Hypothetical particles that interact only through gravity and the weak nuclear force, one of the most elusive and delicate forces known to physics. WIMPs would be heavy and slow-moving, giving them the gravitational heft needed to shape galaxies without interacting with ordinary matter. Others suggest that dark matter could be composed of particles called axions, strange, lightweight particles that might behave like a field instead of individual particles. Axions could fill space like a mist, subtly influencing the behavior of ordinary matter without ever directly touching it. There are even more exotic ideas. Theories of shadow particles, sterile neutrinos, and hidden dimensions, all possibilities in the quest to explain what dark matter truly is. Despite decades of research, countless observations, and a relentless search for clues, dark matter remains an unsolved mystery. We have yet to detect a single dark matter particle, despite building ultra-sensitive detectors buried deep underground and sending probes into the emptiest regions of space. Every attempt to catch a glimpse of dark matter through collisions, cosmic rays, or particle interactions has come up empty. It's as if the universe is playing a cosmic game of hide and seek, where the answer is always just out of reach. But the lack of direct evidence doesn't mean we're in the dark. By studying the way galaxies move, how light bends around massive objects, and the distribution of matter in the universe, we can map the fingerprints of dark matter across the cosmos. It's like trying to find a hidden creature in a forest. Though you can't see it, you can track its movements by the rustling of leaves and the snapping of twigs. In this way, we know that dark matter is out there, haunting every galaxy, influencing the formation of stars, and shaping the very structure of the universe. The properties of dark matter, its invisibility, its inability to clump, its gravitational grip, make it one of the most tantalizing puzzles in all of science. It's a reminder that the universe is stranger than we can imagine, filled with forces and phenomena that defy our expectations. Yet, dark matter is also a beacon of hope, a sign that there are still profound mysteries waiting to be solved and that the cosmos is far from giving up all its secrets. In every corner of the universe, from the nearest galaxy to the farthest star, dark matter whispers of a hidden reality, a shadowy universe intertwined with our own, a reality we have yet to fully understand. What is dark matter? It's a question that has led scientists to create the most sensitive detectors ever conceived, hidden away in underground laboratories, miles beneath mountains, far from any interference. These detectors are modern-day treasure chests, filled with incredibly sensitive materials designed to catch a whisper of a particle that may not want to be found. Among these underground experiments are massive detectors like LUX Zeppelin and Xenon 1T. These experiments use giant vats of liquid xenon, a rare and inert gas, kept at frigid temperatures. This xenon is like a net, waiting for the faintest ripple that might signify a dark matter particle passing through. If dark matter exists, as many scientists believe, as WIMPs, weakly interacting massive particles, then every so often, one of these particles should collide with the xenon atoms, creating a tiny flash of light or a subtle change in the electrical charge that the detectors can pick up. But detecting dark matter is like trying to catch a single raindrop in the middle of a hurricane without getting wet. Cosmic rays and other particles are constantly bombarding the Earth, creating background noise that could drown out the faint signal of a dark matter particle. That's why these detectors are buried deep underground, shielded by thousands of feet of rock to block out any interference. Even then, scientists are left sifting through mountains of data, searching for that one clue that might reveal the existence of a dark matter particle. A painstaking and patient search that can take years, even decades. Meanwhile, above ground in Geneva, Switzerland, another kind of search is underway at the Large Hadron Collider, the world's most powerful particle accelerator. The LHC is a colossal machine, stretching 17 miles in circumference, where particles are smashed together at nearly the speed of light. This violent collision creates an energy so intense that, for a fraction of a second, the conditions resemble those of the universe just after the Big Bang. In this extreme environment, scientists hope to create dark matter particles in a controlled setting, observing them as they momentarily come into existence before disappearing into the fabric of space. The idea is that dark matter could be a byproduct of these high-energy collisions. If the theory is correct, the presence of dark matter particles might be inferred from the missing energy and momentum in the collision's aftermath, like noticing a thief has taken something from a room without actually seeing them. These experiments are the scientific equivalent of a high-stakes detective story, with researchers playing the role of sleuths, piecing together the evidence left behind by invisible particles. The search doesn't stop there. Some scientists believe that dark matter might emit faint, almost undetectable signals, subtle whispers of radio waves, gamma rays, or other exotic radiation. In orbit around Earth, Space telescopes like the Fermi Gamma Ray Space Telescope are scanning the sky, hunting for these signals that might point to regions of dark matter annihilation or decay. They look toward the center of our galaxy, the Milky Way, where dark matter is thought to be densest, hoping to catch a glimpse of its elusive fingerprint. Despite decades of searching, despite billions of dollars invested in state-of-the-art detectors, particle accelerators, and space observatories, the dark matter particle has remained just beyond our grasp, a cosmic enigma that taunts us with its presence. It's as if the universe has hidden the answers behind a curtain, giving us only the faintest hint of what lies beyond. Every experiment, every observation, brings us a step closer to understanding what dark matter is, but each step reveals how much more we have yet to learn. And yet, the lack of direct evidence hasn't deterred scientists. Each null result is a clue in itself, narrowing down the possibilities of what dark matter could be. We now know, for example, that dark matter doesn't interact with ordinary matter in the same way as other particles, and we've ruled out many possible candidates. Every failed experiment refines the search, making the mystery even more compelling. The hunt for dark matter is a testament to human curiosity and the drive to understand the universe at its most fundamental level. It's a story of perseverance, of scientists digging deeper into the mysteries of reality, chasing after something they can't see but know is there. The search is a grand experiment, involving thousands of researchers across the globe. Each piece of data is a potential breakthrough, each detector a new hope for understanding the invisible forces that shape our universe. If dark matter is ever detected, if we ever manage to isolate a single dark matter particle and study its properties, it could revolutionize our understanding of physics. It might lead to a new era of science, revealing secrets about the nature of the universe, the formation of galaxies, and the fundamental forces that govern reality. Until then, the search continues deep underground, in massive particle colliders and in the silent emptiness of space. A cosmic mystery waiting to be solved, a puzzle that could change everything we know about the cosmos. Gravitational lensing, dark matter's fingerprint. Picture yourself gazing at a distant galaxy, a smudge of light that has traveled across billions of light years to reach our telescopes here on Earth. Now, imagine that there's a colossal cluster of galaxies standing in its way, somewhere between that faraway galaxy and our observatory. You might think that this cosmic obstacle would block the distant light, but something extraordinary happens instead. The light bends. It curves around the massive cluster, creating a visual illusion that allows us to see galaxies hidden behind it. This is the strange and beautiful phenomenon known as gravitational lensing. Gravitational lensing isn't just a trick of perspective. It's a consequence of Einstein's theory of general relativity. According to Einstein, gravity isn't just a force, but a warping of the very fabric of space and time. Massive objects like galaxy clusters bend this fabric, causing light to follow the curve like a river winding through a valley. This distortion acts like a giant cosmic magnifying glass, amplifying the light of distant galaxies and revealing them in ways we would never be able to see otherwise. But gravitational lensing does more than create beautiful images. It provides a window into the hidden universe. The gravity that bends the light doesn't come just from the visible galaxies in the cluster. In fact, the amount of bending suggests there's far more mass present than what we can observe. This unseen mass, which accounts for the majority of the gravitational pull, is dark matter, one of the most spectacular demonstrations of gravitational lensing, and by extension, the existence of dark matter, comes from an image known as the Bullet Cluster. In this cosmic drama, two enormous galaxy clusters collided with each other, a cataclysmic event that took place millions of years ago. As the clusters smashed together, the visible galaxies mostly passed through one another like ghosts, while the hot gases within them slammed into each other, creating a shockwave, a bullet of bright X-ray emission. What makes the Bullet Cluster extraordinary is what happened to the dark matter. Unlike the hot gas, dark matter doesn't interact in the same way. It doesn't collide or produce a shockwave. Instead, It passes straight through the collision, staying separate from the visible matter. Using gravitational lensing, astronomers mapped the mass distribution of the bullet cluster, finding that the bulk of the mass, believed to be dark matter, had moved on ahead of the gas in visible galaxies. This separation between visible matter and dark matter is like the universe leaving a forensic clue at the scene of a cosmic collision, pointing directly to the presence of dark matter. Each gravitational lens is like a fingerprint, a unique pattern that dark matter leaves behind, revealing itself not through light, but through its undeniable influence on the universe. Gravitational lensing allows astronomers to observe galaxies from the earliest moments of the universe's history, bringing them within reach of our instruments. These distant snapshots, seen as they were billions of years ago, are illuminated by the power of dark matter, bending the universe's light and acting as a cosmic spotlight, shining on the early days of galaxy formation. For all its mystery, dark matter is a subtle artist working in the background and shaping the grand design of the universe with gentle but firm hands. Gravitational lensing is our way of catching a glimpse of that design, a rare opportunity to study the invisible and trace the shape of the unseen. Every lens image is a piece of the dark matter puzzle, each bending light a clue that guides us toward a deeper understanding of the cosmos. The universe is filled with these dark fingerprints, places where the invisible has left its mark on the visible. It's a testament to the strangeness and wonder of the cosmos, where even the darkest corners are filled with mysteries waiting to be uncovered, one gravitational lens at a time. As we continue to map the dark matter in the universe, we peel back the layers of the unknown, moving ever closer to understanding the true nature of the invisible forces that govern the stars, galaxies, and the very fabric of reality itself. Dark matter halos around galaxies. Imagine galaxies as brilliant islands drifting in the vast black ocean of the cosmos. Each of these islands, including our own Milky Way, is encircled by an unseen force called a dark matter halo. This halo extends well beyond the observable borders of the galaxy, like a gigantic ghostly aura that ties everything together. These halos are enormous, far larger than the galaxies they envelop. If you could see a dark matter halo, it would dwarf the luminous stars and gas, extending outwards for hundreds of thousands of light years, even beyond the brightest galactic outskirts. Despite their enormous size and mass, they are completely transparent, with no light to give them away. The only hint of their existence is their influence, like the unseen currents of an ocean subtly but powerfully shaping everything around them. The importance of dark matter halos cannot be overstated. They are the glue that holds galaxies together. In the absence of these halos, the spinning stars in a galaxy would drift apart, flung away by centrifugal forces. Think of a child's toy top spinning rapidly. The faster it spins, the more force it needs to hold together. Galaxies are no different. Their rotation curves tell us they are spinning at speeds that defy the gravitational grip of visible matter alone. Yet they remain intact, stabilized by the mass of their invisible halos. Our own Milky Way is cradled in one of these dark matter halos, a cosmic cocoon that shapes the very structure of our galaxy. The stars, gas, and dust we see make up only a small fraction of the Milky Way's total mass. The rest, the hidden majority, is dark matter, a silent guardian that holds our galaxy in its vast, unseen arms. Even our solar system, with its familiar planets and asteroids, moves through this halo, influenced by its gravitational pull like a ship sailing through a gentle, invisible tide. Scientists have long been captivated by the nature of these halos, which seem to dictate the cosmic dance of galaxy formation. To understand how they shape the universe, researchers turn to computer simulations, virtual universes created inside powerful supercomputers. These simulations take into account the gravitational effects of dark matter, creating models of galaxies as they would appear over billions of years. The results are astonishing, showing how dark matter halos act as the architects of the cosmos. In these simulations, galaxies don't form in isolation. Instead, They grow within vast clouds of dark matter, tethered together by its immense gravity. Streams of dark matter, like unseen rivers, funnel gas and dust into dense regions where stars ignite and galaxies are born. The halos act as cosmic scaffolding, guiding the formation and evolution of galaxies as they merge, collide, and transform over the eons. Every star in the sky owes its existence to these halos, which provide the necessary gravitational framework for galaxies to coalesce from the primordial chaos of the early universe. One of the most fascinating insights gained from simulations is the discovery of how dark matter halos influence galaxy clustering. Galaxies are not randomly scattered across the cosmos. They gather in groups, clusters, and massive superclusters, all linked together by vast, invisible filaments of dark matter. This network, the cosmic web, is essentially a map of dark matter's influence. Galaxies trace out the skeleton of this web, forming at the intersections where dark matter halos are densest. The halos themselves merge and grow, colliding and pulling in matter to form ever larger structures, from small groups of galaxies to enormous clusters containing thousands of galaxies. The evidence for dark matter halos isn't confined to computer simulations. Observations of real galaxies provide clear, indirect proof of their existence. Astronomers have measured the rotational speeds of stars at the edges of galaxies, far beyond the bright core where most visible matter resides. To their surprise, these stars move just as quickly as those near the center, defying the predictions of Newtonian mechanics. If only visible matter were present, they should slow down. The logical conclusion is that a vast halo of unseen mass surrounds each galaxy, providing the gravitational pull necessary to keep these stars in orbit. One of the most revealing observations comes from studying galaxy clusters, massive collections of hundreds or even thousands of galaxies held together by gravity. The motion of galaxies within these clusters and the bending of light from distant sources, a phenomenon called gravitational lensing, both suggest a staggering amount of invisible mass, dark matter, extending far beyond the visible galaxies. These halos are not only around individual galaxies, but also envelop entire clusters, merging and intertwining in a cosmic ballet that spans millions of light years. There is still much to learn about these enigmatic halos. While we understand their gravitational influence, we are only beginning to piece together their properties. What are they made of? Are they composed of mysterious particles like WIMPs, weakly interacting massive particles? Or could they be something even stranger, like primordial black holes or undiscovered forms of matter that defy our current theories? The study of dark matter halos is more than just a search for what lies in the shadows. It's a quest to understand the underlying structure of the universe itself. These halos tell the story of how the cosmos evolved from a hot, dense state after the Big Bang to the vast, complex universe we see today. They hint at the forces that shaped galaxies, dictated the formation of stars, and even influenced the emergence of planetary systems capable of harboring life. Dark matter halos are the scaffolding upon which the visible universe hangs, an invisible hand guiding the evolution of cosmic structures. From the smallest dwarf galaxies to the grandest galaxy clusters, each one is a silent testament to the hidden forces that have shaped the universe over billions of years. They are the shadows behind the stars, the ghostly frameworks that cradle the galaxies, and the guardians of the cosmic order, waiting for us to unravel their mysteries, one discovery at a time. Dark energy is that storm, an invisible force that not only challenges our understanding of gravity, but also shapes the fate of the cosmos itself. The story of dark energy began in the late 1990s when two independent teams of astronomers embarked on a quest to measure the distance to far-off supernova, brilliant explosions marking the death of massive stars. These teams, known as the Supernova Cosmology Project and the High Z Supernova Search Team, anticipated that as the universe expanded, the light from the supernova would be dimmer than expected, indicating that the expansion was slowing due to the gravitational pull of matter. However, what they discovered was nothing short of astonishing. The distant supernova were not dimmer but brighter than anticipated, This unexpected brightness indicated that they were farther away than they should be if the universe's expansion were slowing down. Instead of gravity pulling everything together, it seemed that the universe was expanding at an accelerating rate, pushing galaxies away from each other. It was a cosmic revelation that left astronomers astounded and prompted a flurry of questions about the very nature of the universe. In the wake of this discovery, the term dark energy was born, a placeholder for this elusive force that was pushing the universe apart. Unlike dark matter, which clumps together and has a gravitational influence, dark energy is smooth and uniform, permeating all of space. It doesn't interact with light or ordinary matter in any way we can detect. Instead, it acts as a driving force behind the accelerated expansion of the cosmos. To grasp the implications of dark energy, consider the universe as a vast balloon. As the balloon expands, points on its surface move further apart from each other. Dark energy is the air inflating the balloon, a constant force that drives this expansion. This process suggests that the universe is not static. It is dynamic and ever-changing, constantly evolving in ways we are only beginning to understand. The discovery of dark energy represented a paradigm shift in cosmology, forcing scientists to reconsider everything they thought they knew about the cosmos. For centuries, the dominant view was that gravity, the force that pulls objects together, should slow the expansion of the universe over time. The notion of a universe expanding at an accelerating pace contradicted this long-held belief and led to the realization that our understanding of the fundamental forces shaping the universe was incomplete. Various theories have emerged to explain dark energy, each attempting to unravel the mystery behind this cosmic enigma. One of the most prominent is the concept of a cosmological constant, first introduced by Albert Einstein in his theory of general relativity. Einstein proposed this constant as a way to achieve a static universe, which was a prevailing belief in his time. When it was later discovered that the universe was actually expanding, he dismissed the constant as his greatest blunder. Ironically, it may now hold the key to understanding dark energy, suggesting that it represents a fixed energy density spread throughout space. Another idea posits that dark energy could be tied to quantum field theories, the theoretical framework that describes how particles and forces interact at the quantum level. According to this view, dark energy arises from the energy fluctuations of empty space, often referred to as vacuum energy. However, calculations of vacuum energy lead to values vastly larger than what we observe in the universe, presenting another profound mystery. Furthermore, there are theories suggesting that dark energy may be dynamic, changing over time rather than remaining constant. These theories introduce the idea of quintessence, a hypothetical form of dark energy that evolves and has varying properties across the cosmos. Quintessence posits that this mysterious force could interact with matter in ways we have yet to fully comprehend, opening the door to a wide array of potential behaviors. As scientists continue to investigate dark energy, they turn to advanced observational techniques and experiments. Projects like the Euclid Space Telescope and the Wide Field Survey Telescope are set to probe deeper into the universe's expansion, gathering data to help unravel the complexities of dark energy. By measuring the distribution of galaxies and the effects of gravitational lensing, researchers hope to shed light on the elusive force that governs the universe's fate. Yet, despite these efforts, dark energy remains an enigma, a testament to the limits of our current understanding. As we push the boundaries of knowledge, the mysteries of dark energy remind us that the universe is full of surprises, challenging our perceptions and inviting us to explore the unknown. It serves as a humbling reminder of how much we have yet to learn about the cosmos. In the grand narrative of the universe, dark energy plays a pivotal role, steering the course of cosmic evolution. As galaxies drift apart and the universe expands, we find ourselves grappling with profound questions about existence, purpose, and the very fabric of reality. With each discovery, we inch closer to unveiling the true nature of this invisible force. But the journey is far from over. In this grand tapestry of dark matter and dark energy, we are reminded that the universe holds more secrets than we can fathom, urging us to continue our quest for understanding, curiosity, and wonder in the face of the unknown. The discovery of dark energy. The tale of dark energy unfolds like a thrilling race against time, a quest that would change our understanding of the universe forever. Picture the scene, the late 1990s, when two rival teams of astronomers, driven by curiosity and ambition, embarked on an ambitious mission to measure the expansion of the cosmos. Their goal was to study type Ia supernovae, cosmic fireworks that erupt with a consistent brightness, serving as reliable beacons in the vastness of space. The Supernova Cosmology Project and the High-Z Supernova Search Team were the two teams racing against each other. With powerful telescopes and meticulous observations, they sought to map the distances to faraway galaxies, hoping to uncover the secrets of the universe's expansion. As they pointed their instruments toward the night sky, they meticulously recorded the light from these distant explosions, calculating how far away they were based on their brightness. However, the results they found were nothing short of astonishing. To their disbelief, the type Ia supernovae appeared dimmer than they should have been, indicating that they were farther away than expected. This discovery suggested that, rather than slowing down, the universe's expansion was actually accelerating. The implications were profound and shocking. What force could possibly be causing this acceleration? As the astronomers delved deeper into their data, a revolutionary concept began to take shape. The realization that a mysterious force was at work in the universe sent ripples through the scientific community. They named this force dark energy, a term that would become synonymous with one of the greatest mysteries in cosmology. In 2011, the groundbreaking findings of these two teams were recognized with the Nobel Prize in Physics, solidifying their place in scientific history. Yet, while they celebrated their achievements, they also opened a Pandora's box of questions that would challenge our understanding of the universe for years to come. What exactly is dark energy? How does it interact with the fabric of the universe? Why is it causing galaxies to race apart at an ever-increasing speed? As scientists grapple with these profound inquiries, the discovery of dark energy redefined our perception of cosmic dynamics and the ultimate fate of the universe. This newfound understanding painted a picture of a universe in turmoil, where the forces of attraction, usually dominated by gravity, were now being counteracted by an unseen repulsive force. The universe was not just expanding. It was expanding faster and faster, hinting at a future where galaxies would drift further apart, leaving behind an increasingly isolated cosmic landscape. The implications of dark energy are both inspiring and unsettling. It suggests a cosmos that is not static or predictable, but rather dynamic and ever-changing, governed by forces we are still struggling to comprehend. As researchers continue to explore this enigma, they are driven by the desire to understand what dark energy means for the universe's future. Will it continue to expand forever, or could it one day lead to a dramatic fate, such as the Big Freeze or the Big Rip? In this cosmic narrative, dark energy represents the final frontier of our understanding, urging us to look deeper into the shadows of the universe. The quest to decipher the nature of dark energy is ongoing, a thrilling journey filled with discoveries, debates, and the promise of revelation. As we continue to explore the mysteries of our cosmos, dark energy remains a powerful reminder that, in the vastness of space, there is still so much we have yet to uncover. The universe, with all its wonders and secrets, beckons us to embark on this extraordinary adventure of discovery, inviting us to unravel the mysteries of existence itself.